Alright, today we're going to still continue to talk about acids and bases and talk about it from the perspective of a titration. Okay, and with a titration, what you're going to get is a couple of things. Number one, a titration from a definition standpoint is going to be written right up here. Alright, a titration is used to find the concentration of a solution using a concentration of a known solution. Okay, and so pretty much what happens in, sometimes we will see M1V1 equals M2V2. So it's a little bit different. We may know a volume and a molarity. We may know a volume and we're solving for a molarity. But a couple of terms we need to be familiar with. Analyte is a solution with an unknown concentration. Okay, and we don't know the concentration, that's our analyte. Our titrant is what we're solution with the known concentration. It's also called our standard solution. Okay, now there's a couple other terms, definitions that we need to describe. First off is an equivalence point. An equivalence point is when equal numbers of moles of an acid and moles of a base are present. Okay, so when they're exactly equal, you have what's called the equivalence point. We've essentially neutralized. An endpoint is when the color of an indicator changes. And the equivalence point of a reaction is usually marked by the color or an endpoint of an indicator. Okay, and we're going to use, we've seen some indicators when we use the pH paper and the cabbage juice. They changed color to tell you what pH things were. So it's kind of the same idea. Now, if acid-base indicators, like we said, are used to mark the endpoint of a titration or the equivalence point, it only works if you choose one whose endpoint is the same as the equivalence point. And that's a little above what we're going to do this year, but typically, most often, they're usually complex molecules that can act as very weak acids. And so usually what means is it will change colors, and that's what's going to happen, because in a neutralization reaction, we're not going to have our, if we're taking an acid and a base, really general here, we're making water and some salt. Okay, so sodium chloride or whatever we've got. You're not going to get bubbles, you're not going to get a precipitate, you're not going to get energy, but if we add an indicator, we can get a color change. So we're kind of using that to our advantage to let us know when the chemistry is over. And this is an example of an indicator called bromethymol blue. And more importantly, what you need to know is that for this one, okay, it starts off as yellow. Okay, so over here we have an acidic situation. And as you start to add more hydroxide, okay, we would be adding hydroxide in here. So in went the hydroxide, and as we started to add it, it would essentially neutralize all of that acid, and then once extra hydroxide was added, we would get the blue color, and that would indicate that the reaction was over and that we neutralized everything. Now, you do not have this chart, nor do you need to be able to familiarize yourself, but just know that there are lots of different indicators that have color changes across the pH spectrum. So pretty much whatever color change you're looking for, you can find one for. Okay? Now, so you guys don't have that, but you don't need to worry about it. Now, other pH indicators which we've seen, universal indicator is something that will change color. This particular one can be from 4 to 10. We also use red cabbage juice, which showed the whole gamut. It went from 1 to 14, and there's other ones out there that have wider ranges as well. pH paper is essentially pH paper soaked in a universal indicator, and we use that, compare the color of the paper to match the pH to figure it out. And then we use the pH meter. The way the pH meter works is it actually measures the voltage between the electrodes to find the pH, and that's because with pH we're measuring hydrogen ion concentration, so it does a lot of math to figure out the voltage in order to generate a pH value for it. Okay, so that's essentially the terminology for titrations and what indicators are. Okay, now we're going to switch gears just a little bit and talk about the math related to titrations, and then we're going to see about doing some lab stuff on this as well, alright? And it won't let me write on this, of course it won't. So, what we need to do first of all is talk about why neutralization and titration are important. So I'm going to read this little piece over here. It says nearly all of the adult population suffers from acid indigestion at some time. Although hydrochloric acid is always present in the stomach, an excess can cause heartburn and a feeling of nausea. common way to relieve the pain of acid indigestion is to take antacids to neutralize the stomach acid. Okay, we've talked about this. Neutralization is simply taking two dangerous things, turning it into water and salt. So an active ingredient in many antacids is sodium hydrogen carbonate, which is a fancy word for baking soda, aluminum hydroxide, or magnesium hydroxide. In this section, you'll learn what a neutralization reaction is. Okay, so over here for our neutralization, nope, I want to keep that way. Okay, for our neutralization reaction, what you have, perhaps, is in an acid-base reaction, the acid donates a proton. Okay, we know that. Now, neutralization reactions, I'm just going to talk you through this just to give you a little bit of background, and then we'll do some of these in class the next time that I see you. So as a reminder, neutralization reactions, when solutions of an acid and a base are combined, the products are a salt and a water. Okay, so a salt and a water. Now here is our full reaction. Hydrochloric acid gives us sodium hydroxide, gives us sodium chloride, and water. So the full net ionic equation, if you split everything up, okay, hydrochloric is a strong acid, so it does split. So you have hydrogen plus chloride, sodium and hydroxide, sodium chloride, and then water. So the net ionic equation becomes simply hydrogen ion plus hydroxide gives us water. So this is the whole idea of where we can neutralize something, because we take two really dangerous things and we make salt and we make water. Now, if it comes to stoichiometry, we're going to do a little bit of stoichiometry related to this stuff, is that ultimately stoichiometry problems involving neutralizations of acids and bases are the same concepts as when we did solutions. That's all stoichiometry means down here. For example, one of the ways that we can get from volume to moles is using molarity. Okay, and we'll do lots of samples of these in class, but if you can get from volume to moles, then it's still looking at the mole ratio. Whether you use the chart, whether you do dimensional analysis, that's still how you figure out stoichiometry, is using a mole ratio. So for example, the sample that you guys have down here, it says how many moles of sulfuric acid are required to neutralize 0.50 moles of sodium hydroxide. Now they just did moles to moles here, okay? So for example, our known is that we have 0.50 moles of sodium hydroxide. Our balanced chemical reaction looks like this, okay, where you have sulfuric acid plus 2 sodium hydroxides gives us sodium sulfate salt and water. Now the mole of sulfuric acid to sodium hydroxide is 1 to 2. Okay, now this shows dimensional analysis over here. I'll show you the chart method in just a second, but in essence, since it's dimensional analysis, you have 0.50 moles of sodium hydroxide. All you have to do is show the mole ratio. 1 mole of sulfuric acid for every 2 moles of sodium hydroxide tells us we have 0.25. Now the other thing, you can start to see some connections here simply because the mole ratio of sulfuric acid to sodium hydroxide is 1 to 2. The expected number of moles of sulfuric acid should be half the given number of moles of sodium hydroxide. 2 sig figs, because that's what we started with. So in essence, there's no limiting reactant. We can use it to figure out how much is there. Okay, so what I have here is just to show you chart-wise. Now remember, what the question was asking was if I was given or had 0.50 moles of sodium hydroxide, they wanted to know how many moles of sulfuric acid were needed to neutralize it. And the last slide showed you dimensional analysis, but the other way you could have done this, if you take 0.5, divide it by 2, you get 0.25, you bring it over, 0.25 times 1 tells us that we needed 0.25 moles. Okay? Now the other piece that I want to just show you really quick is that sometimes it won't give you moles. Okay, remember, we know with moles, we know how to go back and forth with grams. We know how to go back and forth with number of atoms. Okay, we've learned how to go back and forth to liters of a gas with either PV equals nRT or 22.4 liters per 1 mole if it's at, 1 mole, if it's at standard temperature and pressure. Now we got to add one more piece to go from moles to liters of solution. Okay, and the way that you use that is you use molarity as a conversion factor. Okay, and so for example, the way that you want to do this, and you want to jot this down somewhere because you don't have a slide for it, so you need to have evidence that you've written it down and that you've watched it. For example, if we had a solution that was 0.500 molar, and we know that we had 2.5 liters of it to make it simpler. Okay, we can use molarity as a conversion factor, and here's why. Because if I have I want to know the moles of the substance. Well, if I start with 2.5 liters, remember molarity is exactly the same as moles per liter. Okay, so I take my 2.5 and multiply it by the molarity, 0.500 moles over 1 liter. Okay, and when I do this math, I get 2.5 times 0.5. So it's going to give me 1.25 moles of whatever substance that I was doing. Now, if you hate that, well, you can go right back to the molarity equation, moles per liter, so that you knew that your moles, or your molarity, was 0.500 equals moles over 2.5 liters. The math is exactly the same. You're still going to end up with 1.25 moles. Okay, so we also